In this video, we will have a look at the t-SNE method, which can be used for visualizing high-dimensional data in, for example, 2 dimensions. t-SNE or t-SNE stands for T-Distributed Stochastic Neighbor Embedding, which is a method that captures local structures of high-dimensional data while also revealing the global structure, such as the presence of clusters. The t-SNE method was published in 2008, and the equations that I will show at the end of this video are given according to this paper and from Wikipedia. I will first show some applications where t-SNE can be used and compare it with principal component analysis. Then we will have a look at a simple example that explains the basic idea behind t-SNE, before we go into the mathematical details. We will first see how t-SNE and PCA perform on the classical MNIST dataset, which contains thousands of images of handwritten digits. Every row in this dataset contains pixel values for each image. The first column shows which digit the image contains. For example, the first row represents an image of a handwritten 5, whereas the second row represents an image of a handwritten 0, and so forth. Each image is a square that contains 784 pixels, which means that each image or row has 784 columns in addition to the first column. Suppose that we like to generate an image of the data that is located on row number 6. We would then put the elements in column numbers 2 to 29 here, then the next 28 elements here, and so forth, until we have a square matrix with 28 rows and columns. This image is supposed to represent a handwritten 2. We will now use t-SNE and PCA to compress these 784 columns into just 2 columns and plot these columns in the 2-dimensional plot and label the points so that we can see which point that corresponds to a certain digit. Just like PCA, t-SNE is an unsupervised method because it does not use these labels in its computation to identify the groups. This is an example of a t-SNE plot of 10,000 images in the MNIST dataset. Each point in this plot represents one image. For example, this point represents the following handwritten 8, whereas this point represents a 4. We can see that the t-SNE plot separates the images of the 10 digits quite well. In comparison, this is the corresponding PCA plot of the MNIST dataset, which fails to separate the digits. I will explain why in a minute. t-SNE plots are commonly used in single-cell RNA sequencing to visualize high-dimensional gene expression data in 2 dimensions to identify clusters of cells with similar expressed genes. Each point in this t-SNE plot represents a single cell. Points in the same cluster can be seen as cells that have a similar gene expression profile. Such a cluster of cells therefore usually represents cells of the same cell type. For example, the clusters may represent different cells in our immune system. If we were to use PCA on the same dataset, the clusters would not separate well. So, why is this the case? Well, one reason is that a PCA plot usually only shows the first 2 principal components, because these explain most of the variance. By illustrating only the first 2 components, which in this case only explain about 5% of the total variance, we lose a lot of information that is stored in the other components. For example, we can see that clusters 2 and 6 are not well separated based on the first 2 components. If we instead plot component 1 versus component 5, clusters 2 and 6 are now well separated. The t-SNE method does not hold important information in several components like this. Instead, it includes all information into just 2 dimensions, which explains why the t-SNE plot better shows the clusters that exist in the high-dimensional data. However, the t-SNE method is computationally expensive, which is why it is sometimes combined with PCA. One can therefore compress the variables by first using PCA and select, for example, the first 30 to 50 components that store most information, and then computing the t-SNE plot based on these components instead of all variables. Another reason why PCA might fail to separate the existing clusters is that it is a linear method. For example, if we were to project this nonlinear two-dimensional dataset in one dimension, the clusters will not separate well with PCA, whereas the t-SNE method would do a good job in separating the existing clusters, because it preserves local nonlinear relationships. All of these points are fairly close in the global geometry. t-SNE tries to preserve the local neighborhoods. Points that are close have a high probability of being neighbors, which means that these points have also a high probability of being neighbors, and so forth. Another example where t-SNE is commonly used is to visualize word embeddings. This is the same data that I showed in the video about transformers. The GPT model had about 12,000 embedding dimensions. If we were to compress thousands of word embedding dimensions into just 2 by using t-SNE, we would get a plot like this, where every point represents a word or a token. For example, this plot shows 5,000 words. Similar words are close in this t-SNE plot because their high-dimensional embeddings have similar features or contextual meanings. So, when you see a t-SNE plot like this, you can interpret it like points that are close together in the t-SNE plot were likely close neighbors in the original high-dimensional space. However, you should not use the plot to compare distances between clusters. For example, 8s and 6s in MNIST dataset are here far apart, although they are expected to be close in a high-dimensional space, since such handwritten digits should be quite similar. Also, do not try to interpret the numbers on the axis, because these values do not mean anything. We will now have a look at a very simple example to illustrate the basics of how t-SNE works before we go into its exact mathematical details. Suppose that we have the following simple three-dimensional dataset with 5 data points, which can be visualized like this in a three-dimensional scatter plot. We see that data points 4 and 5 are close, whereas data points 1, 2 and 3 are close. The idea is to project these data points into 2 dimensions, so that we can visualize the data in a simple 2-dimensional scatter plot. In t-SNE, the high-dimensional space refers to the original data, whereas the low-dimensional space is a simplified representation that preserves the local similarities between the points. The method starts by calculating the Euclidean distance between all data points of the original data. For example, if we were to calculate the distance between data points 1 and 5, we would plug in the x, y and z coordinates in this equation and do the math. We now plug in the rounded Euclidean distance in the distance matrix. If we calculate the distances between all data points in our dataset, we would get the following values. For example, we can see that the Euclidean distance between data points 2 and 4 is 5.2. Then we might normalize these distances by, for example, dividing all the values by the maximum value in this matrix, so that we get the following values. Next, we place 5 data points at random coordinates in a 2-dimensional space and calculate the Euclidean distance between the points. For example, to calculate the distance between data points 1 and 3, we plug in the x and y coordinates of these 2 data points and do the math. Next, we normalize the distances by dividing by the maximum value in this matrix, so that we get these values. The reason why we normalize is that we can now better compare the distances. Data points in high dimensions have generally longer distances to each other than in low dimensions, which explains why we normalize the distances. The idea is now to move around these data points so that the normalized distances in 2 dimensions are as close as possible to the normalized distances in the high-dimensional space. For example, we can see that the normalized distances between data points 2 and 3 differ quite much in the high and low dimensional space. Let's move this data point from here to here and recalculate the normalized distances. We see that the distances now become more similar to the normalized distances in 3 dimensions, which means that the points in the 2-dimensional plot now better resemble the points in the high-dimensional space. If we continue to move around the data points, we might end up with the following plot that looks quite similar to the plot in 3 dimensions. We also see that these 2 matrices now have similar values. We will now have a look at the math behind t-SNE. The method starts by calculating the Euclidean distances between the data points in the high-dimensional space, just as we did before. The distances are here shown with 2 decimal places. Note that I also fill the upper triangle of this matrix, and you will see why soon. So these values are the same, because they both represent the distance between data points 1 and 3. Next, we square the distances. We will now calculate the conditional probabilities, where these terms correspond to our squared distances. This formula can be used to calculate the normal distribution. So what we have up here is similar to this part of the formula for the normal distribution. So the numerator can be seen as the height of a normal or Gaussian distribution for a given distance between 2 data points, where sigma squared represents the variance, which controls the width of the normal distribution. To simplify the calculation, I will here use a fixed value of sigma, so that these 2 terms are equal to 1. In t-SNE, the value of sigma is not fixed and is related to the so-called perplexity parameter that I will explain at the end of this video. Let's apply this formula to calculate the conditional probability in row 2, column 1. We plug in the squared Euclidean distance between data points 1 and 2 here. What we get in the numerator can be seen as the height of the Gaussian curve for the squared Euclidean distance between data points 1 and 2. Then we plug in the values of the second row in the denominator, but not for the distance between a data point and itself. This term can be seen as the height of the Gaussian curve based on the distance between data points 1 and 2, and this is the height based on the distance between data points 2 and 3. The heights that correspond to the distances from data point 2 to data points 4 and 5 will be super small. If we do the math, we get the value of about 0.39, which we plug in into a matrix with conditional probabilities. If we compute the whole matrix, we'll get these values where each row now sums up to 1. So this row can be seen as conditional probabilities that data point 1 would pick one of the other 4 data points as its neighbor. For nearby data points, the conditional probability is high, whereas for data points further away, the conditional probabilities will be super small for reasonable values of sigma. So the t-SNE method can be seen as it uses large pairwise distances between dissimilar data points and small pairwise distances between similar data points. Note that the values for data points 1 and 3 are different. One therefore computes the average of these 2 values and also divides by the sample size. In this case, we get a value of 0.11 that we plug in here. Then we compute the same for the other elements. We now have a symmetric matrix where all its values now sum up to 1. We are now done with all the calculations for the high-dimensional data. Let's put it here as a reference. Next, we place 5 data points in a 2-dimensional space with random coordinates, which explains why t-SNE is a stochastic method, because the initial coordinates will be different every time we create a new plot. Then we calculate the squared Euclidean distances between the 5 data points in the low-dimensional space. We could now use the same equation based on the Gaussian distribution as we used previously, where sigma is set to 1 over the square root of 2, so that this equation no longer depends on sigma. However, we will then generate an SNE plot, which tends to squeeze the points too much, which causes the crowding problem as explained in the t-SNE paper. They therefore used a formula based on the t-distribution with 1 degree of freedom, which will generate a t-SNE plot. The t in the name t-SNE therefore refers to the t-distribution. The reason for instead using the t-distribution with 1 degree of freedom is that it is wider compared to the Gaussian distribution. So, to compute the value of the Q matrix, for example for the third row, first column, we plug in the squared Euclidean distance here, and all the other values in this matrix that are not included in the main diagonal in the denominator. We then fill in this value in the Q matrix. If we do the same calculations for the other elements in this matrix, it will include these values, which should sum up to 1. So the idea is now to move around these data points, so that the values in the Q matrix become as similar as possible to the ones in the P matrix. This can be done by minimizing this cost function. If the values in the two matrices are identical, the value of this ratio will be equal to 1. And since the log of 1 is 0, the cost function would then be equal to 0, which means that the two matrices are identical. Let's plug in our values, except for the values in the main diagonal, to compute the value of this cost function. We see that our cost function results in a value of 0.77. What is interesting with this cost function is that it will generate a large penalty for a large Pij if the corresponding Qij is too small. This means that the cost function mainly focuses on the corresponding errors for points that are close in the high-dimensional space, which is one reason why t-SNE strongly preserves the local neighborhoods. To reduce the value of this cost function, we can use the method of gradient descent. We therefore need to compute the derivative of this function. This is the derivative of the cost function that we can use in the gradient descent method. How to derive this function can be found in the original t-SNE paper. These are our P and Q matrices, and the y's are the coordinates of the given data points in the low-dimensional space. We now plug in our values in this function for the first row, where I is equal to 1 and j is equal to 2. Now, j is increased by 1, which means that we take the corresponding values in the third column. Then we increase j to 4 and 5 and do the math, which here show values from calculations with more decimals. Then we increase I to 2 and do the same calculations. If we do the calculations for all rows, we will get these values, which we plug in the gradient descent formula, where alpha is the learning rate that we here set to 1. These are our current coordinates in the low-dimensional space. In the paper, they also added a momentum term for a smoother update, but we will not use that term here. So, if we subtract these values from these values, we'll get these updated values. And the coordinates of the data points will be updated like this. With these updated values, we have reduced the cost function from 0.77 to 0.56. We then iterate like this until we reach some convergence or until we reach the maximum number of iterations. After 100 iterations, I got the following plot that closely resembles what we see in the high-dimensional space. After 100 iterations, these are the values in the Q matrix, which closely match those in the P matrix. So the main idea with the t-SNE method is to minimize the difference between the distances based on the conditional probabilities in the high and low dimensional space, to preserve both local and global structures in the data. Finally, we will discuss the perplexity hyperparameter. Remember that we previously used a fixed value of sigma. t-SNE does not use the same sigma for all points. So for each point, we find an appropriate value of sigma, so that 2 to the power of the Shannon entropy of the conditional probabilities is approximately equal to the chosen perplexity parameter. A larger perplexity parameter generally results in larger values of sigma. The recommended value of the perplexity parameter is in the range of 5 to 50. So, here are 3 plots of the MNIST dataset, which show how the perplexity parameter changes the plots. If you set the perplexity parameter to 5, the clusters are much closer than if you set a larger value of the perplexity parameter. So, you need to try a few values of this parameter until you find an appropriate plot that you like to show. Note that there is a related method called UMAP, which produces similar plots as the t-SNE method. I will explain the UMAP method in a future video. This was the end of this video about the t-SNE method. Thanks for watching.